Okay, as you know then, to solve this equation, we first solve the homogeneous equation, and then depending on the nature of the function here, we, if possible, and it will be possible for just about anything we consider in this course, we use undetermined coefficients to solve the non-homogeneous equation, and if that fails, then we attempt to get a solution using variation of parameters. That leads us to a solution, but we can't always integrate the functions that we get, so that solution doesn't always come out in closed form. It might come out as an integral. In any case, we have those two options, and again, for the circuits we deal with here, we're going to use mostly undetermined coefficients. There are also applications, for example, square wave applications, where we would want to use Laplace transforms to solve this. And that's actually quite a simple, that leads us to quite a simple type of solution as soon as you understand a little bit about Laplace transforms. But it's not clear that all our courses are going to cover Laplace transforms. So I might do that as a supplement to give you a reference, but we're going to stick for now mainly to sine and cosine functions for the source. Okay, so we start in any case not worrying about the source voltage function, but solving the homogeneous equation. Here's the equation. We divide both sides by L, and this is very straightforward. Of course, we can't do that if L is 0, but if L is 0, we just don't even have this term, and we just end up with a first order equation with an exponential solution, a real exponential solution. Okay, well, we've got this equation, the characteristic equation assuming Q equals e to the mt. Now I used Q equals e to the RT previously, but in deference to people who are using the book that our instructor here has chosen, I'm going to use e to the mt because that's what they use, so everybody will have a constant here that they're comfortable with, either in the solution for mechanical systems we did earlier or the solution for electrical systems. In any case, it's very straightforward. The characteristic equations m squared plus r over lm plus 1 over lc equals 0. And we get m equals negative r over L plus or minus. Well, I'm not going to read it to you. You can write it out. You should write this out before you even look at it. Okay. Okay. Having written this out, you'll agree in one way or another. And of course, I got the over 2 here. It's kind of obscured by the fact that I had to bunch things up a little bit down here. Now, I chose to go ahead and factor out r over 2L. So you can verify that if you factor out r over 2L, this is what you get. Now, I got this, and I really didn't like the looks of it, because I haven't looked at this since last time I taught this course, which was in class, which is 2 years ago. Didn't get a whole lot from my distant students, a whole lot of questions about this sort of thing. And my differential equations distant students haven't questioned it a whole lot. So I didn't like the looks of this. I wanted to see an RC. But that's just because if you reduce this, you get a 1 over RC here, and RC becomes your time constant and stuff that we don't have to worry about right now. I didn't like the looks of that. So I went ahead and worked out the units of 4L over R squared C to make sure that those units, well, that equation came out to be unitless. Now, it might be a little hard to read what I've written here, but I don't know. The camera sometimes enhances what we've got. L has units of what? Well, if you look at L, L times Q double prime has to equal, have to have the units of voltage. So that L has to have units of voltage over units of Q double prime. Units of Q double prime, Q is charge. Q prime will be charged per unit of time. Q double prime is charged per unit of time squared. In SI units, that would be coulombs per second squared. So that L has units of voltage divided by coulombs per second squared, which I've written here. Now you should stop and reduce this to fundamental units: kilograms, meters, seconds, and coulombs. Coulombs aren't really fundamental, amps are fundamental, but we're going to reduce it to coulombs anyway. Coulombs used to be fundamental, and it's just kind of easier to deal with coulombs because amps are coulombs per second. Coulombs, of course, then are amp seconds. Well, let's not worry about it. Okay, voltage is joules per coulomb, and we divide that by our coulomb per second squared. That should be fairly readable. Okay, and that comes out what? Joules times second squared over coulomb squared, just by getting rid of the second squared down here, putting it in the numerator. A joule is a kilogram meter squared per second squared. So a joule second squared is a kilogram meter squared, so we get kilogram meter squared over coulomb squared. That's the unit of L. The unit of, let's go to R. Q prime is in units of coulombs per second, so R is going to be in units of voltage divided by coulombs per second. Voltage divided by coulombs per second is, and you can make the transition, joules per coulomb squared times seconds. And if we simplify that, a joule is a kilogram meter squared per second squared, so the joule to second is going to be a kilogram meter squared per second, and we have the coulomb squared in the denominator, so R is in kilogram meter squared over coulomb squared seconds. Capacitance is in units of coulombs per volt. The C here and the C here might be a little confusing, but when you go to units, C stands for coulombs. And that's coulombs divided by joules per second. And something's wrong with what I'm looking at, so I'm going to pause. Okay. I got a coulomb squared there, and I was reading that as a second, and I wasn't getting the coulomb squared, although I know I have to get a coulomb squared, so I had to kind of resolve that, which is my sloppy writing. That's joules over coulombs. So the coulombs over joules per coulomb becomes coulomb squared per joule. A joule is a kilogram meter squared per second, so that's going to give us a kilogram meter squared in the denominator. The second is going to come up into the numerator, so we have coulomb squared second over kilogram meter squared. And over here we get L over R squared C has to be in units of kilogram meter squared per coulomb squared, the unit of L, divided by the square of the units for resistance, which is going to be kilogram squared meters Q to the fourth over coulomb to the fourth second squared, which is what we have here, times the unit for capacitance, which is coulomb squared second over kilogram meter squared. We have that here. Maybe a little hard to read. I can't even read it except that I know what it says. But if we write that out and do that, we see that we have kilograms in the numerator. We have kilograms squared over kilograms in the denominator, so we have kilograms in the numerator and kilograms in the denominator, so the kilograms go away. We have meters squared here. We have meters to the fourth over meters squared here, which gives us meters squared. So we have meters squared over meters squared. The meters go away. We have coulombs squared over, well, we have coulombs squared over coulombs to the fourth in the denominator. That's coulomb squared. So we have, well, reciprocal coulomb squared. We have reciprocal coulomb squared in the numerator, reciprocal coulomb squared in the denominator, so that goes away. So now this is unitless, which it had better be since it's being subtracted from the unitless number 1. Now I'm going to pause here and go on with the analysis, but right here's what we get from the characteristic equation. Here's our solution. We're probably going to use this more than this, but the advantage of this solution is that it shows you how the coefficient m here compares with r over 2l, negative r over 2l, of course. It's got to be negative because this is going to be a decreasing exponential. If this square root here is close to 1, then it doesn't differ much from the behavior of the system, where m was just equal to negative r over 2l. Now, if this is complex, well, you're going to get into a complex valued solution. You're going to get sines and cosines, as you should understand at this point. We'll go on in a minute and work out some more details.